Quantum teleportation's huge leap. Here's what you need to know. Imagine sending not just a message, but the actual quantum essence of an object, its precise quantum identity, across incredible distances, almost in an instant. Picture a form of communication so secure, it's practically eavesdrop-proof by its very nature. This isn't just a cool scene from your favorite sci-fi flick. This is the rapidly unfolding reality of quantum teleportation. And get this, scientists have just smashed through old barriers, pulling us closer to a future we've mostly just dreamed about. Intro. Hey everyone, and welcome. Today we're jumping into the wild world of quantum mechanics to check out a mind-blowing new achievement in quantum teleportation. Now let's be super clear, we're not talking about beaming people around Star Trek style. Quantum teleportation is all about transferring quantum information, the state of a qubit, which is the basic building block of quantum computing, from one spot to another, without the particle itself making the trip. It's all based on the wonderfully weird and often counterintuitive rules of the quantum universe. For years, this has been a really fascinating idea, but mostly stuck in labs. But the latest breakthroughs? They're not just tiny steps, they're giant leaps. We've seen teleportation over mind-boggling distances, clever new methods that are way more efficient, and even quantum information zipping through the same fiber optic cables that power our internet right now. Today we're going inside the lab, so to speak, to see exactly how researchers are pulling off these amazing feats, step by step. We'll look at how they whip up entangled qubit pairs and use something called Bell measurements to transfer these super delicate quantum states, really stretching what we thought was possible. So, stick around, because the future of how we communicate and compute is being written as we speak. Section 1. The Quantum Toolkit: Qubits, Superposition, and Entanglement. All right, before we can really get our heads around how quantum teleportation works, we need to get familiar with the basic tools and ideas. These are the fundamental bits and pieces that this incredible technology is built on. First up, let's talk about qubits. You know how in regular computers information is stored in bits, which are either a 0 or a 1, like a light switch that's either off or on. Well, qubits are the quantum version, and they're a whole lot more flexible. A qubit can be a 0, a 1, or, thanks to a wild idea called superposition, it can be both a 0 and a 1 at the exact same time. Think of a coin spinning in the air. It's neither heads nor tails until it actually lands and you look at it. A qubit's kind of like that. Its state is a mix of possibilities until you measure it, which forces it to pick one. And it's this mind-boggling ability to be in many states at once that could give quantum computers their incredible processing punch. Now let's throw in another concept that'll bend your brain a bit. Quantum entanglement. This is probably one of the most famous and frankly weirdest parts of quantum mechanics. When two or more qubits get entangled, their destinies are linked, no matter how far apart they are. If you measure the state of one entangled qubit, you instantly know the state of the others, even if it's hundreds of kilometers away. Albert Einstein famously called this spooky action at a distance. It's like having two of those spinning coins, and the second one lands on heads, you instantly know the other one, miles away, has landed on tails without even looking. This instant connection is super important for quantum teleportation. Now, this doesn't mean information is zipping faster than light and breaking the rules of relativity, because, as we'll find out, you still need a regular, old-fashioned communication channel. But the connection itself, that's immediate. Finally, we should quickly touch on Bell states and Bell measurements. A Bell state is a special kind of super-entangled state that two qubits can share. There are 4 of these Bell states, and they're a basic way to understand entanglement. A Bell measurement is a type of quantum measurement you do on 2 qubits that pushes them into one of these 4 Bell states. This measurement is a really key part of the teleportation process because it helps us grab information about the relationship between the qubit we want to teleport and one half of our entangled pair. So, to sum it up, We've got qubits that can be in multiple states at once, superposition. Qubits that can be mysteriously linked no matter the distance, entanglement, and special measurements, Bell measurements, that help us figure out these entangled states. With these gadgets in our quantum toolkit, we're ready to see how teleportation actually happens. Section 2. The Teleportation Protocol, a step-by-step journey. Okay, now that we've got the basics down, let's walk through how quantum teleportation actually works. Typically, scientists use the names Alice, she's the sender, Bob, he's the receiver, and let's say the qubit Alice wants to send the state of is qubit X. Step 1. Getting an entangled pair ready and shared. It all starts by creating a pair of qubits, let's call them qubit A and qubit B, that are entangled, often in one of those Bell states we just talked about. Think of these as our special linked coins again. Alice keeps qubit A, and qubit B is sent over to Bob. Bob could be in another lab, another city, or even, in some really cool experiments, on the other side of a satellite link. This sharing has to be done super carefully so that the delicate entanglement doesn't break. Step 2. Alice works her magic, the Bell measurement. Alice now has two qubits, qubit X, the one whose unknown quantum state she wants to send, and her half of the entangled pair, qubit A. She then does a joint measurement on qubit X and qubit A. This is that important Bell measurement. This measurement does a couple of things. First, it reads some info about how qubit X and qubit A are related. Second, and this is a biggie, the measurement itself changes the original states of both qubit X and qubit A. In fact, the original state of qubit X is actually destroyed at Alice's end by this measurement. This makes sense with something called the no-cloning theorem in quantum mechanics, which says you can't make a perfect copy of an unknown quantum state. The Bell measurement gives one of 4 possible results. These results can be written down as 2 classical bits of information, like 00, 01, 10, or 11. Step 3. Old school communication. Alice calls Bob. Alice then takes these 2 classical bits of information she got from her Bell measurement and sends them to Bob. This is done over a normal communication channel. It could be an email, a phone call, a laser pulse, pretty much any standard way of sending data. And this step? It's limited by the speed of light. So while the entanglement connection is instant, the whole teleportation process isn't faster than light because of this classical communication part. Step 4. Bob's turn, rebuilding the state. Bob, waiting patiently, gets the 2 classical bits from Alice. Depending on which of the 4 results Alice sent, Bob performs a specific quantum operation on his qubit, qubit B, which remember was originally entangled with Alice's qubit A. For example, if Alice sent 00, Bob might not need to do anything. If she sent 01, he might use a specific type of quantum gate, like an X gate or a Z gate, which are basic moves in quantum computing, on qubit B. And here's where the cool part happens. After Bob does the correct operation, based on Alice's classical message, his qubit B transforms and takes on the exact quantum state that Alice's qubit X originally had. The quantum state of qubit X has been teleported from Alice to Bob. Qubit X itself didn't go anywhere. Its information, its very quantum identity, did. It's a pretty neat dance between entanglement and classical information, letting a quantum state be transferred without physically moving the particle that was holding it. Section 3. Major breakthroughs, pushing what's possible. The process we just walked through is the theory, but the real buzz is around the recent experiments that are making quantum teleportation stronger, able to go further, and more practical. 1. Conquering distance and going hybrid. For ages, scientists have been trying to teleport quantum states over longer and longer distances. Early experiments were just across a few meters. Then came fiber optic links stretching tens of kilometers. A huge moment was the Mindscape satellite, which allowed quantum teleportation between ground stations in China and Austria, over 1,200 kilometers apart. This really showed the potential for a global quantum communication network. More recently, there's been some really cool work with what hybrid entanglement. This is where entanglement is shared across different properties of particles, like a photon's polarization, the direction its electric field wiggles, and its path or frequency. And here's a wild twist. Some of these hybrid setups have shown that certain kinds of noise, the stuff that usually messes up quantum information and makes teleportation worse, can actually boost the fidelity, the accuracy, of the teleported state. This totally unexpected finding, where noise actually helps get almost perfect teleportation, turns old ideas on their head and could lead to tougher quantum communication systems that work well, even in noisy real-world situations. Second, teleportation over the internet cables. We already have. One of the biggest recent steps forward comes from researchers who've successfully teleported quantum information over existing, busy fiber optic internet cables. A team at Northwestern University, for instance, pulled this off over a 30-kilometer fiber optic cable that was already carrying loads of high-speed internet traffic. This is a total game changer. Before this, most people thought we'd need brand new, separate fiber optic networks for quantum communication. The worry was that the delicate single photons used for quantum stuff would just get lost in the flood of light particles carrying normal data, like trying to ride a unicycle down a 6-lane highway. But by carefully picking specific wavelengths of light where there's less interference, and by using fancy filtering techniques, these teams have shown that quantum and classical signals can share the same highway. This makes it way easier and cheaper to build quantum networks, meaning we could potentially use the massive web of existing fiber optic cables to create a quantum internet. How cool is that? Third, new and smarter experimental methods. Scientists are also getting clever with the methods themselves. For example, researchers at the Max Planck Institute of Quantum Optics figured out a way to use just a single photon to teleport the spin state of an atom to another atom 60 meters away. This method uses very few resources and can be scaled up, which is super important for building bigger quantum networks with lots of nodes. Other experiments using trapped ions, atoms with an electric charge, have achieved what's called deterministic quantum teleportation. That means the teleportation works every single time. They run the experiment, not just some of the time, and with really high accuracy, better than what you can do with just classical methods. These often involve a source qubit, a helper qubit, and the receiver's target qubit, which is entangled with the helper. These breakthroughs, from teleporting over huge distances and through noisy real-world internet cables, to creating more efficient methods with single photons and atoms, are all incredibly important. They're shifting quantum teleportation from a cool physics curiosity into something that could become real, practical technology. Section 4. Why this matters. The huge implications. So, we can teleport quantum states. Why is this such a big deal? Well, the implications are massive and could totally change things in computing, communication, and even how we understand the universe. First up, quantum computing. Quantum computers have the potential to solve certain problems way faster than any classical supercomputer we have today. But building large, reliable quantum computers is a massive challenge. Quantum teleportation offers an essential way to send quantum information between different parts of a quantum computer, or even between separate quantum processors. This could effectively link them up to create more powerful, distributed quantum computing systems. Imagine a quantum computer built like Legos, where different quantum chips can share their quantum states super efficiently. Teleportation is a big part of making that happen. Second, secure communication and the quantum internet. Because any attempt to spy on a quantum communication channel that uses entanglement automatically messes up the system, quantum teleportation can be a cornerstone for fundamentally secure communication networks. If someone tries to intercept the teleported information, the entanglement breaks, and both the sender and receiver can be alerted. This is the foundation of quantum cryptography and could lead to an unhackable quantum internet, a network where information is sent with a level of security we've never seen before. This is getting more and more important because our current encryption methods might not stand up to the power of future quantum computers. Third, fundamental research. These experiments aren't just about cool tech. They're pushing our understanding of quantum mechanics itself. They let us explore the nature of entanglement, information, and the very fabric of reality at its deepest level. Some physicists even think that studying quantum teleportation and entanglement could give us clues about huge mysteries like the nature of space-time or the black hole information paradox. Being able to reliably teleport quantum states also makes new things possible in quantum sensing and metrology, leading to incredibly precise measurements of physical quantities. And while it's still pretty out there, these principles might one day even be useful in areas like transmitting energy. The recent progress, especially in making teleportation work over existing cables and in noisy conditions, tells us that these applications are moving from what-if ideas to actual engineering challenges. We're really setting the stage for a future where quantum technologies are woven into the fabric of our information world. We've explored the strange and wonderful world of qubits and entanglement, walked through the steps of the quantum teleportation protocol, and seen the incredible breakthroughs that are making it a reality. From sending quantum states across continents with satellites to beaming them through the busy fiber optic cables under our cities, scientists aren't just tweaking a curious phenomenon, they're literally building the future. Quantum teleportation isn't just sci-fi anymore. It's a fast-moving field that's set to shake up computing, secure our communications, and give us a deeper understanding of the universe. Scientists are really pushing the envelope, and the next few years are going to be incredibly exciting to watch. So, what part of quantum teleportation just blows your mind the most? Are you hyped about the idea of unhackable communication or the thought of computers powerful enough to solve today's biggest mysteries? Let us know what you think in the comments below. And if you found this peek into the quantum realm as fascinating as we do, please give this video a thumbs up, subscribe for more explorations into the cutting edge of science and technology, and definitely hit that notification bell so you don't miss our next adventure. Thanks for watching.